All right, we got a simple embedded device here, Arduino Uno. It has an atmega328p microcontroller chip inside it that drives all of the ports here. And we're going to be interested in how a program gets loaded from a computer or something else to the memory of the microchip. We are going to implement a bootloader for that. So, alright, embedded platform developers frequently upload programs to their development boards, usually for testing a change in their source code or trying out a new program. Uploading a program can involve a dedicated programmer device in addition to the development board. In this setup, the main computer is connected to the programmer device. I'm not going to connect it right now, but assume it's connected. And the programmer is in turn connected to a special SPI header, the 6-pin header here, like this. And the main computer talks with the programmer, and the programmer, on behalf of the computer, programs the microchip here. Alright, although this is a valid way to upload programs to your development board, it can be considered too much work as it requires setting up the programmer and the subsequent connections every time you want to upload a new program. Also, a dedicated programmer device may not always be available. Because of these reasons, more often than not, a bootloader is used to upload programs to an embedded device. In this setup, the main computer is directly connected to the development board. The bootloader is configured to get program data from the main computer and load it on the program memory for execution. We should note that a bootloader is a special program that runs on the same chip that it loads programs to. It's in the same address space. This is called self-programming. Bootloader support on an embedded platform depends on two things: the ability to communicate with a computer and self-programming support. Well, Arduino Uno and Nano platforms support these features, so we can write a bootloader for them. In fact, most Arduino devices are shipped with a pre-installed default bootloader. But to learn how to control this process at the lowest possible level and for fun, I wrote my own bootloader. Let's upload a program, right? So we've got a tool called AVR Dude, and I think I've got a program here. Yeah. So this program just does in a loop. It's just blinks this default LED here. The PB5 is the port location of the LED. It toggles it every time this X variable hits 250,000 the value, right? So let's change this. Let's increase the period to 1 million, right? So, and let's compile this program and upload it. So to upload a program like this, before uploading, at the compilation stage, we have a hex output. So this is the hexadecimal binary output in Intel formats. So this is the actual binary of our program. So how do we upload it? Well, after you connect your development board to your computer, you usually want to learn its port name. In Mac, I use this command after plugging in my USB, and it's going to say something like this. These two names refer to the same thing, but I'm going to use the one above, right? So this is going to be my port, and I'm going to pass this to a program called AVR Dude, which stands for AVR uploader downloader program. It's just a tool to upload and download programs to an AVR architecture microcontroller, which Arduino Uno has one, the atmega328p. So let's write the command. Actually, I have the command. I'm just going to explain what it does. I'm going to explain the flags. The -c flag specifies a configuration file for different boards, different programmers and stuff. A configuration file with the default installation of the AVR dude comes with it. So I'm just going to use that. We usually don't want to change anything in that, so it's of little importance for us right now. We're going to enable verbose output. I'm going to come to the -v in a second. With -p, we're going to pass in the type of the processor we're going to program. Right now, it's an atmega328p, as we discussed. We're going to pass the programmer type. So our programmer type is called Arduino, and this means the bootloader inside the chip that Arduino ships with the Uno board. So it's actually a program. It's not a physical programmer like this one. It's just the bootloader program. So it's software. And we're going to specify the ports in which we are going to communicate. It's just this. And we're going to specify a baud rates. Why are we specifying a baud rate here? What's the significance of it? We're going to see it shortly, but well, briefly, baud rate means amount of bits that you can pass through a UART connection in a second. And we're going to disable auto erase option with this flag. Auto erase means erase the chip and then write something. So we don't want to erase everything on the chip. Yeah, and with this flag, we're going to upload to the flash memory. We're going to write it. We're going to write to flash memory this file, this hex file here I just opened. And we're going to inform AVR that it is in Intel format with this E, with this I, right? So -v, what does -v do? Well, I'm gonna come to it in a second, but first let's just upload the program. So I run this command, the flash is written, and if you paid attention, this LED is now blinking more slowly. Well, what does the AVR do? Help, if this works. What does the -v do? I actually forgot it. Well, -V. Yes, do not atomic. Yeah, it just disables the verification. So we don't need verification right now, so we're going to disable it. So if we don't disable it, it also tries to verify the program that it uploaded. So it's going to take more time, but it's going to be more reliable, I guess. Well, we uploaded the program, we changed the behavior here, but what actually happened? Let's go find the schematic of the Uno board and let's examine what's going on here more closely. So this is the schematic of the Uno board. In here you can see the atmega chip, that's a square chip right here. It's got 32 pins. And we've got USB header here, and the USB header here is this one, where we plug in this USB cable. And one thing you might notice, the USB does not directly connect to the atmega microcontroller chip, right? Because the microcontroller chip does not have any pins for USB. It does not understand USB natively. So we need a converter chip from USB to a communication protocol that the microcontroller understands. And the microcontroller understands UART and SPI. In Arduino Uno, we've got a USB to UART converter chip called CH340G. Maybe in your Arduino Uno, it's maybe a different chip, but the main idea is the same. It just converts USB data to our UART data, right? So with the cables, you can trace the cables and you can see the data pins connect to here, and then the UART pins, TX, RX, are actually connected to the microchip directly, almost directly. We just got a like resistors here, something. All right, so that's the communication, but we also need a way to actually program the memory here. So let's talk about the memory on the atmega chip. So it's a microcontroller. It can do arithmetic operations, ALU operations. It can do jumps, functions, interrupts. It's got an interrupt routine too. But it does not come with like a protocol for understanding UART data to understand the data coming from the UART and program itself accordingly. That's the bootloader software's job. So usually what Arduino Uno manufacturer does is they burn a bootloader program here that understands the UART data coming from the AVR tool from the computer, and with that protocol, AVR issues some commands and burns or writes the program I just written to the memory of the atmega chip. And here's an illustration directly from the datasheet, by the way, of the program memory. So we've got 32 kilobytes total of program memory in this chip, in this microcontroller, right? So this number here is the address of instruction, and one instruction is 2 bytes. So you should multiply this number with 2 to get the maximum amount, the maximum size of the program memory, which is 32 kilobytes. And the memory is actually separated into 2 sections. There's application flash section and boot flash section. And with the name boot flash section, you might get some ideas that our bootloader program must reside in this boot flash section, and you will be correct. Application code usually resides in here. It's got a lot of space here. And boot flash section resides in a restricted, even more restricted space than the 32 kilobytes. Usually you can configure it to be 2 kilobyte, 1 kilobyte, or even as small as half a kilobyte. The bootloader shipped with Arduino Uno fits in half a kilobyte, so it is configured to have a boot flash section of half a kilobyte and 31.5 kilobytes for application flash section. So you can upload programs up to 31.5 kilobytes in size inside of the atmega328 chip for an Arduino board. But if you want to use a more capable bootloader, you can increase its size to up to like 2 kilobytes, but then you're going to have less space for your application. So there's a trade-off there. And we're going to see how we can configure the chip to have boot flash section, to the boot flash section size. And there's also a configuration for from where the first instruction after a power up executes from. It can execute from here, the address 0, the start of the application flash section, or it can execute from the start of the boot flash section. If it starts from boot flash section, it automatically runs your bootloader code or the code you upload to the boot flash section. And usually the code inside the boot flash section has special privileges through configuration to modify the program memory of the application flash section. So this code here that runs here uses special instructions that modify the program memory of the application flash section. So the code here and code here is kind of different, right? All right, so we're going to see how I structured my bootloader program. It's actually the same thing. It uses the same protocol as the OptiBoot bootloader program that is usually shipped with the Uno board, but it's a little bit smaller and it's a little bit different, right? And by way of talking about my program, the bootloader program, I'm going to actually talk about how a program gets linked, how a C program in an embedded environment is actually compiled, linked. We're going to talk about that, and maybe that's more like general stuff that you might find useful if you're not necessarily into embedded programming. Well, let's actually... All right, there's one thing that I didn't talk about. A bootloader is a program that resides in here that is used to upload programs here, right? So how do you upload a bootloader? Well, how do you upload a bootloader without a bootloader, right? There's kind of a chicken and an egg problem. What you do then is you use a dedicated programmer device like this one here. If you want to upload a bootloader, you want to burn the bootloader onto the microchip. If that's your approach here, you kind of must use a dedicated programmer. And this programmer has a 6-pin connection here that connects to the SPI header, or I think it's called ISCP header. So sending the appropriate signals at this header, you can issue special commands that change the configuration of the microchip, load program to a microchip, and do pretty much everything that the microchip allows you to do. A bootloader might not be that powerful. Usually a bootloader program as small as half a kilobyte only works for uploading a program, reading the program, and pretty much that, like, and maybe reading the signature bytes or something. So the bootloader program is simpler, it's tinier, it's more convenient, but it's less powerful. A dedicated programmer is more powerful. You can do more with it. And to upload a bootloader, you must use a dedicated programmer. So what we're going to do is we're going to examine how I structure my code, and we're going to examine the data sheet to learn how a bootloader works, how the boot sequence in that particular configuration where the first instruction executes from here works. And after that, we're going to have an understanding of how a bootloader works in the Arduino Uno board. So let's make my project. I'm in my project. We can just call make here. I think. All right. I think we have an error here. All right, so AVR IO H is not found. That is interesting. That is interesting. Well. might be because of this environment variable, right? So AVR tell where is AVR GCC to CC? I should have a command here. All right. So the thing is this, right? I need to pass a variable called I need to pass the compiler here. So let's delete this. The compiler is a special one. It's not the general GNU compiler, but it is the AVR GCC. So it's a GCC wrapper for AVR architecture microcontrollers like this one. And we need to use that compiler. What I did back then was I just called make, and my CC variable was the default CC or GCC, and GCC did not understand AVR headers or anything, but AVR GCC understands. So I'm gonna clean my project, then I'm gonna call make with the CC variable, which is AVR GCC. All right, this should work, and it worked. We've got a binary hex here, main hex of size 424 bytes, which fits inside the half kilobyte restriction in the boot flash section. So let's look at the code again. Let's look at main C, right? So this is not, so I'm going to talk about how my indexer works. The indexer is not like a must, but with VS Code, with how I program, I use the C-lang C indexer, and I find it very convenient. So, well, I've got a make file here. It's a little bit complicated, but not that much. So I got a build system, right? I got calls to AVR GCC. I found a program called bear, which listens to the build commands from your build system, be it make or CMake or anything else. It listens to the compiler calls and generates a compiler commands JSON database. Here we're going to see a compile command JSON right here. So that database is what C-lang D indexer uses. So let's go back to main C now, and maybe restart the extension. All right, so my indexer works now. And what the compile command JSON does is it's a database of how each of my source files gets compiled and what they get compiled into, what defines they include, and so on. So this is very useful because, for example, these are my headers, right? They have this character, but the headers with this one, like this, they are system headers which come from AVR GCC. They are not a part of my project, but they are considered system headers for me. And these system headers use defines to like include or exclude code for specific CPUs, specific types of AVR CPUs, AVR microcontrollers. This is most prevalent in the AVR I/O section, which is like, look at this code. This code is huge, and all it does is if you have a specific CPU, you're going to like include its header. That's all, right? And I know this is highlighted because my compile commands JSON told it this is going to be compiled with this flag, and this flag corresponds to these defines. So this is open. It's very convenient. I like the C-Lang D indexer a lot. Another feature of the C-Lang D is I hover over a header and it displays what I use from that header in this source file. It's very nice. It's very nice for like understanding how the code works. If I go to a function, it's gonna tell me you are using this function from this header. It comes from this header. So it's very useful. All right, enough about the compile commands JSON and the C-Lang D. Let's continue on the project. So before diving into the code, into the actual code, I want to go inside the makefile and explain how I structured the program, how I structured the makefile. So we got some variables like the processor name. We're gonna pass the processor name to the flags, the defined flags. We're gonna pass this to AVR GCC, and the AVR GCC will understand that my clock rate is 16 megahertz and my microcontroller name is this one. Because of this, I see this. So you can make the connection there. And I've got some other tools like object copy, size, object copy for copying the object files, size for sizing, querying the size of the object files. Like here, I know that my output hex file is 424 bytes. That's because of the AVR size utility. And now AVR object dump is for examining the object file output of my source files. They're here. Okay, so these are just extra utilities. They are not related to compilation, but after compilation. I got a binary directory here, right here. I got a linker directory, which I store my linker scripts, but we're going to talk about that later. I got my code directory. Everything inside this code directories get compiled and linked. So my source directory, whatever is in my source directory gets linked. Let's actually clean this. So these four source files get compiled, they get linked. And the include directories is self-explanatory. The include directory, I've got one directory, and inside here, all of my headers are here. IOH is associated with IOC, main C is not associated with anything, UART C is associated with UART. Watchdog timer unsafe is obviously related with VDT unsafe. But we've got like two other headers. One is optional. I'm not going to talk about optional right now, but there's another one called small boot. I actually wrote this myself, copying from the official, copying from the system headers. These are functions for like page writes, for writing, actually writing to the flash memory of the program memory in the microchip. But the functions that came with the AVR GCC, the library functions actually use 4 bytes instructions for this operation. But in my chip, in my case, I can use the 2 bytes variants. So that's why I implemented these privately and not use the system, the library functions. We're going to talk about these two. So as you can see, this is assembly code, and we're going to use some assembly code too. Well, let's go back to makefile. I got some options for compilation. I've got an option for optimizing for size, because as I said, size is at the memory is at premium here. We got total 32 kilobytes, and our bootloader program needs to fit inside a half a kilobyte. We got link time optimization on as a compilation flag. We got linker options, which is like a relax option. We're going to talk about it. No start files, excludes default default linked object file like interrupt vectors and stuff. We're not gonna include interrupt vectors inside the boot section, so we don't need this. And I'm gonna do like experiments. We're gonna examine the binary here. Let me generate the binary again. So the main elf, I want to see the main elf dump. So we have some sections here. This is our code. We're gonna examine it. We're gonna change some flags and see how the final elf file changes, right? So we're gonna understand why we need these flags. We got dependency flags here to help the make tool, the make command, to associate header files as dependency to the source file. So if I change a header, it's going to compile the corresponding C files again. Otherwise, it's not going to do it. There's also define flags, which I explained. One is for clock, one is for the device name. And then we're going to have compilation flags here. I just open all warnings. This is just a warning flag. And for each of the include directories can be understood as a list. Right now, I got only one include directory, but I could have more, right? For each include directory, apply the include flag here, include the options here, the compilation options, which is like optimize for size and link time optimization. Add the dependency flags at the compilation stage and define flags. All right, and we got link options, but as you can see, link options is not here. This is for define. This is for compilation. And then I got my C files list. What are my C files? Every file inside of the code directories. So inside the code directory, I'm gonna wildcard search every file that ends with .c, and those are my C files as far as the make file, this make file is concerned. So in this case, those are IOC, main C, UART C, and VDT unsafe C. This is a list of size 4 here. And the object files that are targets that we're going to build will come from the C files. This just substitutes the prefix of every .c file with a .o suffix. So in our case, objects is going to be io.o, main.o, uart.o, and vdt-unsafe.o. This is also a list of size 4. And the dependency files of every C file is also similarly constructed. The dependency files come from this. All right, we've got dumps, and I use dumps for examining the output of the object files. So I also generate the dumps, the object dumps. And our final executable, our final target is main.hex. We actually need to somehow burn the main.hex to the microchip to actually use our bootloader. This is our bootloader, right? And right now it's right here. It has a dump and so on. So main hex is created from main elf. So main elf needs to be created. After main elf is created, we use AVR object copy, which copies some sections inside the elf inside a hexadecimal file in Intel format. So if you open this, it's actually a readable one, and it's got binary data here, all of the instructions here with Intel hexadecimal format. And AVR dude understands this Intel format here. We used it in this command, right? We flash writed a program called this with the format Intel hex. So let's continue. How does the main elf get generated? A main elf is generated from object files. Remember, objects is a list of size 4. It corresponds to io.o, main.o, uart.o, and vdt-unsafe.o. And it's going to get linked from these object files. And I use a specialized linker with the link options. Link options were defined here, right? We're going to talk about them too. And we're going to talk about the linker I use. I actually use a specialized linker here. This flag says use this linker. Do not depend on the default linker. And we need to modify the linker because by default a program gets links at the 0 location, but our program is not a default program. It's a bootloader program. It's going to be loaded inside here, the start of the boot flash section, which is half a kilobyte up from the very bottom of the program memory. So that's why I need a linker script. So that's how you obtain a main elf. If you want to obtain a .o file of any kind, just use the corresponding .c file and compile it with the AVI GCC and the C flags, right? This is self-explanatory. If you don't know this one, just open up a makefile tutorial. You're going to see the symbols. It's a very simple command. You just, to make a .o file, just compile a C file. For clean is self-explanatory, cleans all of the object files. And I've got an interesting one here called disassemble. So disassemble directive actually makes human readable object dumps from object files. So yeah, what do we do here? We're going to create main hex dump, main elf dump, and other dumps here with the AVR object dump utility. And we're going to examine them. All right, so let's examine the elf dump. All right, so let's look at the first instruction. The first instruction is exclusive or the R1 register. And if you go to main, that's actually my first instruction. Exactly that one. So this is the behavior I want from my compiler and linker. The first instruction of this function needs to correspond to the first instruction of my program in a whole. In the end, right? I got a lot of other functions. I got this function, but this function's first instruction is not the first instruction of the final executable. I hope that makes sense. The reason for that is this address actually corresponds to here, exactly the start of the boot flash section. Because inside this chip, we configure the boot flash section size to be half a kilobyte. So this is going to be 31.5 kilobytes address. All right. After this function goes along. We've got some intermediate functions because we're using link time optimization. We're going to play with it too. So yeah, this is how the program gets made. Maybe we can look at the linker script. So before looking at the linker script, let's remove the usage of linker script here. So this is gonna cause it to use the default linker script. And let's see what happens, right? Let's make it and look at the elf dump here. All right, so first of all, my program now starts from the address 0, which is not what I want. This is not an application program. It now starts from here, but that's not what I want. So linker is actually responsible for shifting the starting point from 0 to 31.5 kilobyte address. What is it other than this, what is it responsible for? If you pay attention, this instruction is not the first instruction of my main function. So the linker script is actually configured to elevate the main function to be the first function that gets run, to be the first instruction to gets run in the microchip by placing it to the start of the boot flash section. So it does two things. One, it shifts this from 0 to 31.5 kilobytes, and it elevates this function to be the first instruction that runs. Let's see how the linker script does that. So linker script here, a linker LD, actually includes another LD which contains some configuration. Let's look at them. Let's look at this one, right? So we're going to define some regions, some memory regions. We've got a text section, which is what we're interested in actually. It starts from 0. Its size should be like 32K, I think. Text region length here. Oh well, it's 128K, but it doesn't matter right now because the size defined in the linker script is higher than the actual memory. So it doesn't matter a lot, right? So we got our text section right here. We got our, actually this is not section, but these are memory locations, and we've got a variable called bootloader start, which corresponds to the 31.5 kilobytes address. So how does linker LD use these variables? Well, the linker LD defines sections called text and data, which are standard sections to have in an ELF file. Text holds your program, data holds your RAM, right? So what this means, if you're not familiar with the linker script syntax, this means the text section starts at this location. And what was this location? It came from memory LD, and this is 31.5 kilobyte address. So text section for this program, if you're using this linker script, starts from 31.5 kilobyte range. So we said that linker script does two things. It shifts the start of my program to the appropriate address. It does it by this line, by this actually. And it makes the first instruction, the first instruction of this function, right? So it does that by this. So what does it mean? This means from the input object files, link or like merge the contents of these sections in this order. So merge the bootloader init section, merge text sections, and merge other text sections from the input object files. In my main.c, I actually put this function in a specialized section with this attribute. in my code, right? So this function is special. It's in a special section, and that section is loaded initially into the final text section. So that's how I do. So that's how I make sure that my bootloader init function is called initially. So if I put this here and inside the make file, just like let's reset the change I made on the make file and run this again. So we're going to see that the program is shifted. The program is shifted to appropriate place, but the first instruction is not the one I want. So this is going to execute wrong because the CPU, the microcontroller, is going to start at this address. It's going to execute this instruction, but it's just a utility function here. It's not the entry point of my program. If I reinstate this like here and I recompile, we're going to see my bootloader in function is the first, is the entry point, and it starts from here, so everything is good. So this is why I need a linker script. I need a custom linker script, right? That's the reason. So I actually learned about linker scripts with this project, which is pretty cool. So what else? What else? Well, we can talk about the makefile, and we can talk about the flags, right? So the OS flag, which optimizes the project for size. So let's delete that and rebuild. As you can see, formerly my object file size, my hex file size, my binary file size was 424 bytes, which was fine. It was less than half a kilobyte. We were cool. But now, when I omit the optimization flag for size, I get more than 2 times of that size here. So that's a very important flag for our case, because the space is at a premium in this environment. So there's link time optimization. I'm gonna put the link time optimization to last because I know less of it. I'm just gonna talk about what it affects, right? Or maybe let's just talk about it. Okay, so link time optimization. Let's remove it and observe the effects of removing it. Link time optimization differs the optimization of the C files. So C files get converted to object files, right? So if omit the link time optimization flag, the object file dumps actually makes sense. The IOC has 2 functions, a pointer at the global. And when I examine the dump, I see that function, I see another function, and in the data section, I see a pointer here. All right, that makes sense. That's pretty good. This makes sense, actually. But if we enable the link time optimization, let's discard my change here to get the link time optimization flag back and recompile. And let's check the io.o again, the dump. So it's a very long object dump here. And there's a lot of like GNU, LTO, link time optimization, symbol tab, and there's all kinds of things here. So what this is an intermediary description of my translation unit, the C file. It's an intermediary representation. It's not compiled exactly, it's just an intermediate. So these intermediate representations are going to be used for deferring certain optimizations at the final linkage stage, where we get the main elf. So that's the difference. And by deferring the optimization to the final stage, the compiler can better examine which functions are still used. Are there dead code? Can I cut the dead code out? And it's pretty useful. So if we omit the link time optimization flag and recompile, we get a text size of 500. This is still okay. This is still less than half a kilobyte, but it's on the edge, you know. So if you want to add another feature, we're probably not gonna implement it in 16 bytes or 12 bytes. So that's why we use link time optimization flag as a compiler flag. All right, and there is another link time flag called mrelax. So mrelax refers to this. So in the AVR architecture, there are some instructions, some jump instructions. Maybe I can look at here. There are some relative jump instructions and absolute jump instructions, and they vary in size. Relative jump instructions jump to they have less range than an absolute jump instruction, but they are smaller than an absolute jump instruction. This one is 2 bytes and an absolute jump is 4 bytes because the instruction needs to encode the larger range. So mrelax, what mrelax does is it relaxes those jump instructions at the later stage. So when the compiler sees that, oh, this jump instruction or this call instruction can be squished down to a relative call or relative jump, which is smaller in size, it's going to make that optimization. So if we omit this, I expect the binary size to increase. Let's see, yeah, it increased. It was 424, now it's 492. So that's why we include the mrelax option. Let's also exclude the link time optimization and see what happens, right? So like this is not okay. This breaches our requirements. So like these 3 flags make the program smaller in summary. So no start files is another important one. No start files means do not link the default object file, which includes stuff like interrupt vectors or reset vector. We're not gonna use them. We're going to initialize our program, the CPU ourselves, which is why I initialized this register to be 0. Let's actually remove this and recompile and then examine the main elf dump. So right now, main elf dump starts from bootloader init. And if we omit the no start files, all right, it still works. But why it works is because I have a custom linker here. So if I didn't have a custom linker, the default linker is actually more complicated. It's got more sections here which define the interrupt vector jump tables, the start initialization sections and stuff. So it's more complicated. And if I use that default linker script, I would see that my program is linked with those object files, those standard object files that comes from the library, and they're going to inflate my program size, and it's going to, like, I don't need them. It's going to affect my program correctness too. So let's, I just removed my custom linker flag here. So let's compile this again. Well, it actually did compile. So what's going on here? Let me think a bit. Okay. I got some link options here, which says relax. Look at object files. Okay. Well, all right. Let's do the main elf dump again. So there's the text section. There's the comment section. Well. I don't actually know why the default stuff didn't get linked. What's going on here? So we're not using the default linker. Oh, all right. We are using the default linker. With these link options, we omit the no start files, but we still get this. That is interesting. That is interesting. Maybe it's because of the step that generates the main elf. Possibly. So at this stage, where we link, so let me quickly check how to verbose output for the linker. Linker verbose output. So okay. Okay. So let's add verbose output here. The linker stage. All right. So default linker script needs to be somewhere here. Or maybe actually it's because of the link time optimization. No. Well, all right. I'm gonna get back to it. Okay. So as I know, what I know is the no start files. There's a conflict. Okay. So no start files flag, it just removes the need for the default start or object file to be linked, which includes stuff like vector tables, interrupt vector tables. So, okay. Actually, I can show it maybe here in my, like, we compiled a program here, right? So this also has a makefile. The program has 164 bytes here. It's got an elf. So inside here we can add flag called no start files, and let's see what happens now. Yeah, 32 bytes. Okay, so this is what happens. Okay, so discrepancy here is the vector tables, start vector, interrupt vector tables, and the initialization stuff that makes C language work. Like C language for AVR assumes that the R1 register starts at 0 and stays as 0. It uses this register as 0 register, although AVR architecture does not specify that. This register could be used for anything else too. But C language in GCC, in AVR GCC, assumes this register to be 0 at all times. So we need to initialize it to be 0 at the start of our program. This is why this instruction is here. And also, C programming assumes a stack management system is in place. So the stack pointer is initialized properly at a proper value. It's not going to automatically do that for you. So the start files actually do that. And if we remove them, we actually gain space, but we lose functionality. So this was a user program. This was not a bootloader. It was the Blink program we used. It actually needs these because that program gets loaded in here in the application file section. So it needs the interrupt vector tables, it needs the start code and that stuff. But I actually don't know why removing it here did not inflate my final executable size. That is interesting. Okay. Maybe it's because of Relax, maybe it's because of OS, but yeah, I don't know. Okay, that's one thing I don't know here. Well, so this is the build script, right? So let me check how much. Oh, it's over an hour now. So let's finish this video here and make another one which discusses the source code, like main.c, what it does, how does it satisfies the protocol, the bootloader protocol. Let's check them in another video. All right, thank you for watching and see you in the next video. Goodbye.